In part D, we're given the binding energy per nucleon for 3 particles. We need to show that the energy released is about 18 megaelectron-volts in this fusion reaction. So we will need to use the equation that energy is equal to the mass defect times c squared. So we need to calculate the mass defect. So the way we can do that is, well, here we're given the binding energy per nucleon, so we have an easier case as we don't need to do really any of this. We just need to find the binding energy of the reactants and subtract it from the products. So what we can do is that we know that on the right side we have the helium nucleus, which is the X particle. It has 4 nucleons, so it will be 4 times 7.074. And from this, we will need to subtract what is on the reactant side. So we have 2 times 1.112 plus 3 times 2.872, which will give us an energy of 17.6 megaelectron-volts. And then in part 2 of D, we hence has to estimate the energy in joules that is released as a result of fusion of 1 kilogram of fuel according to the reaction. So we burn 1 kilogram of fuel here. So what we need to consider here is that we have calculated the 17.6 megaelectron-volts for one reaction. So we need to see how much reactants, what was the mass of the reactants here, and then we see how many of these reactions do we need to get 1 kilogram of reactants. So in this starting reaction, we had 2 protons and 2 neutrons. 2 protons and 3 neutrons. So we will have to calculate the mass of that. Now we know the mass of a proton is 1.673 times 10 to the minus 27. And to this we add the mass of 3 neutrons, which is 1.675 times 10 to the minus 27, which are both in the data booklet, obviously. This will give us 8.371 times 10 to the minus 27 kilograms. So we know that we need 1 kilogram. So if we do 1 over this 8.371 times 10 to the minus 27, we find that we need 1.19 times 10 to the 26 reactions. So that we have 1 kilogram of fuel. So the energy released will be this times the number of reactions, as that's the energy for one reaction. So 1.19 times 10 to the 26 times 17.6, and we convert into electron volts, so it's 10 to the 6, and then we convert into joules, so 1.6 times 10 to the minus 19 will give us 3.4 times 10 to the 14 joules. And then part 3, we're told that the specific energy of a fossil fuel is 10 to the 7 joules per kilogram. And so we need to outline an advantage of nuclear fusion when compared to fossil fuels. And we see that the specific energy, so the energy released per kilogram of fuel, is much larger for fusion. So we get much more energy for 1 kilogram of fuel.